It's 2 o'clock, and just welcome to this first lecture of Introduction to Python, which will be going on for the next approximately 2 weeks. And my name is andersx, and I will be giving the first 3 lectures here. And the first lecture today is about Python basics. So let's jump first to a slide about what we will be doing in this part of the course. So the first, this should actually say 3 lectures, I'm sorry. There were originally 4 planned, but there are only 3 lectures. Yeah, so the first lecture, which is today, is just an introduction and to the whole thing. And we're going to go through some Python basics. And basically, this course assumes that you don't really have any experience with Python whatsoever. So we're going to start with some very basic things. So if you already know Python, I think the first day will be maybe kind of boring, but definitely the next 2 days, you should definitely learn something. And at the end of this lecture, the first lecture, we'll be going through how to calculate some properties of the harmonic oscillator. Tomorrow, Tuesday, we will be going through how to debug your code, how to write functions, and we will write some better code for the harmonic oscillator, and we will go through how to plot things with something called matplotlib. And then finally, on Wednesday, we will go through debugging again, because those are great exercises for learning to write good code. And we'll go through a lot of maths on how to do maths in Python. And for that, we'll be using this library called NumPy. And with that, we can do linear algebra stuff. And we will write a small program to do molecular dynamics simulations. So basically simulating an ideal gas with Python. And we're going to make a video of this. So the first part of the course, it's scheduled to take in total 9 hours over 3 days, and that's including both lectures and the exercises. And I think it'll be around 60 to 90 minutes per lecture, and then about 60 to 90 minutes per exercise. And there's one exercise out after each lecture. So about 2.5 hours per day. And then after the final lecture, there is also another problem set, which is graded, which is scheduled to take around like 90 minutes or something. And the deadline for that is on Sunday. Yeah, so basically about 2.5 hours per day. And I would say it's good that if you do the exercises maybe right after the lecture or the next morning while the lecture material is just still like fresh in your mind. So definitely try to get them done before the next exercise. So a practical note, so almost everything is done in what is called Jupyter Notebooks, and we will use an online service called Google Colab. So we already, I try to send an email out and make a YouTube video with instructions, and I think most of you have got it right now. But I will go through this, how to use this in the lecture as the first thing, so don't fear that you're left behind here. So just a quick introduction. So why are we doing this in Python? So basically Python is used everywhere in science, no matter if you're doing data analysis or experiments and getting some data from there, or you're like statistical analysis, or basically everything. There is a Python package for literally everything. So it's used literally everywhere. And another thing which makes Python easier compared to many other types of code is that you don't have to compile your code. And furthermore, there are interactive tools such as the Jupyter Notebooks, which is very helpful to scientists. So none of us presumably are computer scientists. So yeah, for people like us, it's a good thing to have additional tools to help us write code nice and easy. And in my opinion, it's one of the easiest languages to write code in. And also we can use these Python notebooks yeah, to share results and share your code. Yeah. Okay, so today we will go through this basic introduction, which is coming up next. And also we will go through the basics of Python, and we will program some for loops and how to do summation for these. And then lastly, I have this example where we calculate the heat capacity of the harmonic oscillator. So we basically simulate a diatomic molecule and calculate the vibrational properties of that. And then after the lecture, I'll give a short introduction to the exercise sets. Yeah, the first exercise set. Yeah, so let me just close this here. Yeah. Share. Okay. Yes. So we're going to use this online service called Google Colab. And if you want to follow with me on your own screen, I just have to write to everybody here. To everybody, so go to this link, which I'm posting in the chat right now. It's called colab.research.google.com. So this website here, colab.research.google.com. And this is I can zoom in a little bit so it's easier to see if you have a small screen. So this is where we do all our Python coding in this course. And for instance, you can upload IPython notebooks if you want themselves, or if you have some stored in your Google Drive. But the ones that we're going to use for the exercises, they're stored in an online repository called GitHub. And it happens to be my GitHub. So I will just write the address here. It's andersx/python-intro. And if you hit enter, you should see some hits coming up here. I'm also going to post my link in the chat for everyone to see. And now you can see there are two of these IPython notebooks. And one is the exercises, which you will go through for tomorrow. And the first one, or the second one here, is the code that we'll go through during the lecture today. So if you want to do this on your own laptop or computer during this lecture, I would highly recommend that. So you have both your own code and also the code that I'm presenting from this lecture. At the same time, we can go through the same things simultaneously. So I'm going to click here. And it's going to open one of these Jupyter notebooks. And a Jupyter notebook, if you're used to coding, it's a little bit different than like a code file of from a normal, quote unquote, normal programming language. So a Jupyter notebook basically has their text fields and code fields. So for instance, here, there's a text field where I wrote a headline. If you double click on this, you can actually see, you can change the code. I could write hello here, and it will say hello here. And also there are these text fields, and then there are these code fields. So here I basically print hello Python in Python. And so if you want to run this code, you just press the play button here. You get a warning the first time, I think, but just run anyway. It takes a little while the first time you run something because it has to start up a virtual machine in the Google Cloud. But now you can see it actually executed the code here. Another way you can execute it is by pressing Control Enter, which I prefer because then you don't have to click on your mouse. Okay, so hopefully you should know by now how to run code in your IPython notebook. And I'm just going to go through some very basic stuff here. So just some basic math operations that you'll find in Python. For instance, if you want to add two numbers, for instance, 7 plus 17, you can write that like this. And it prints the sum of 7 plus 17, so 24 here. And the star here is a multiplication. So we can try and run that and see what comes out of it. 119. And of course, subtraction and division. And also powers. So these two stars mean 7 to the power of 17 in this case. So I left a field here just to get you more comfortable with Jupyter notebooks where you can write your own example. So we could, for instance, write print 5 times 10 to something, whatever. And it prints that. So I recommend you just do that just to get a feel for everything. So in Python, we have something called variables, and I'm also going to talk about how to name them. For instance, what I showed here is basically how to use Python as some kind of glorified calculator, which is not normally what we want to use Python for. So often you want to store results and stuff. And for that, we use variables. And here you can see I create a variable called x. And if I write x equals to 7, then I can actually, let me show it here. I can add a code section. If I say x equals to 7, I can then print x here, and it should print the value of x. Here, 7. Great. And we can do the same thing with 17. And for instance, we can store the result of 7 times 17.0, and it should print 119.0, I think. Yep, and that's exactly what it does. Okay, so it's not only numbers that can be variables. We can also, for instance, put a string as a variables. So here I made a string, and a string is basically just a sequence of characters. And here I put hello world, and I call this greeting. Now we can try to print this string. So print greeting, and it says hello world. Okay, so you might see here. Okay, so let's take a look at some of the different data types that you find in Python. Oh, and also, by the way, if you have any questions, feel free to write in the chat underway. And I'm checking this periodically just to see if there are any questions. So feel free to interrupt at any point. Okay, so if you're unsure what type your variable is, so if you don't, somebody gave you a variable called x and you don't know if it's a string or whatever it is. In this case, it's very simple. There is actually a question now. We're using Python 3 encoding, right? Yes, all this is Python 3. I hope that answers your question. Great. Okay, so here we have a variable called x, and we set it to 1. And let's pretend we didn't know what the type of x was. So Python has this function called type, so we can print the type of x like this. Whoops. And then we can try and run it, and it'll say it's a class called integer. So int means integer, and that's just the round numbers or the whole numbers. And you can see if I do 5.0 here, and then I print type y, it's a different type. It's called a float, so a floating point comma number. And also sometimes you're not really sure what comes out. So if I multiply 1 by 5.0, we might want a certain type of number to come out, so we can check that we get the right number out. We can also, let's print w here as well. So it's a float and it's 5.0. So you can see I had an integer multiplied by a float, and that actually also gives a float. So if we can try and do this experiment here. So now that both x and y are integers, and then now we're saying w is an integer multiplied by an integer, and that gives an integer. Now, there are some variables that don't mix. So if we go down here to the next field, we can say x is a string, and here I just call the string hello, and y is 42. So what happens if you try and add 42 to something that says hello? That's what I'm doing here. And yeah, here I print z is, and that's the result. Let's see what happens. And so this is the first error that I've shown you from Python, and trust me, you'll get plenty of these errors, and I also get them all the time. So we have to learn to read these error output messages. Especially tomorrow, we're gonna go into a session where we really learn how to read type error. But here you can see it says type error, and it says type must be a string, not an integer. So basically, complaining that we added an integer to a string. So we could, for instance, if we called it 42 like this, so now it's a string called 42. Yeah, so not all data types work together, but for sure all data types that are numbers work together, and that's most of the data types that you're going to be working with, at least during the next couple of weeks, I think. Yeah. So a quick note on naming. So variable names, they don't have to just be x and y. I could, for instance, make a variable called lecturer name. And normally in Python, we use the convention that you use all lowercase letters, and you use underscores. and yeah, just to have a consistent notation. And yeah, you can see students sleep days until Christmas. So these are just examples of how you can name your own variables. But you can feel free to like use capital letters and all caps and so on. But normally just stick to this notation here. So let's just verify that all these are legal names. And we didn't get any errors here. So that seems to be legal. Just some names that are illegal here. And now you can see we get an invalid syntax here. myvar equals John here. So let's try and fix this because you are not allowed to have spaces in names. So we can, for instance, insert an underscore here and make it a valid name. And the same, it's complaining of here. So Python uses this dash as the subtraction operator, so to take something minus something else. So you're not allowed to use that in naming either. So maybe we call that myvar like this. And now everything runs. Okay, so now we've basically gone through some very basic things on how to use Python just to do like one thing at a time. So now we're going to look into something called for loops. So basically, in the end, we want the computer to do many things. And one of the things you can do is using these for loops. And I'm just going to, here in this field, I have put just one of the most basic for loops you can find in Python. And what this for loop does, it's printing every number from 0 to 19. Let's try and run this and see what happens. And then we can go through the syntax of this. So it prints 0 to 19, and then it has an extra message at the end. Okay, so let's go through the code here. So it says for I in range 20. And you can see there's colon, and on the next line, there's an indentation. And the syntax here is that everything that has an indentation like this will be repeated for every number in this range. So it means for the numbers in this range, it will like go through this loop, print, go back, print, go back, print, go back, print, go back until the end. And once it's done here, there's no indentation here. So it prints 0, 1, 2, 3, blah, 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 up to 19. And then this message at the end here, which has no indentation, is not a part of the for loop. So we can, for instance, imagine if we did this here, if we had an indentation here, it would get repeated. But if we remove the indentation, it does not. Okay, so one question here is, what is this range? So it looks like a function that has the argument 20. So let's do an example. So question, what is range? So range is a function that returns every number from 0 up to 1 minus the last number. So you can print it by converting this range into a list. So here, what I do here is print list range. So if you do this, oh, it was already run, sorry. It will print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So as you can see, this has 10 elements in it. And that's why it's called range 10. So intuitively, you might expect to get numbers up to 10, but Python always counts numbers from 0 rather than from 1. So the first number in Python is always the 0th. And so the 10th number is thus a 9. So yeah, note how range skips the final number. It skips 10 here. So just told you that range normally starts from 0. But in principle, you can start from any number by using 2 arguments. So for instance, if I want to print everything from 10 to 19, so I would put 10 here, print range 10 to 20, because it skips the last one. So this will be 1 less than 20. That would be the max. And you can see here 10, if we run this, 10, 11, 12, blah, 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 up to 19. Okay. So one of the things that these for loops are incredibly useful for, and which we'll be looking more into today, is how to do summation in the computer. So here I wrote a very easy sum to make. So it's number k, which is, there's actually an error here. I apologize. Should be some I here. So it's a sum over I from 0 to 19 here. So it's basically the sum over all numbers from 0 to 19. So just like the example we had here, where we printed all the numbers from 0 to 19, we can make a number k here. So we set k to 0, which is like the start value of k. And instead of printing every number, we can add the number in the list. So in the first iteration, we will add 0 and then 1 and 2 and 3 to the list. So that's what I'm writing here. I have k, I take the k, and then I set it equal to k plus the value of I. So maybe it's easier if I demonstrate this. So let's put this here, print I and k, and then let's see what happens when I run this. So now you see everything that has indentations here will be done every loop cycle. So the first loop cycle, your range starts from 0. So k is 0 and I is 0. So k is 0 plus 0. And then we print I, which was 0 for the first iteration. And then we print k, which was also 0. So that's a 0, 0 here. Then the next iteration, it's 1. So we add a 1 to k here. So k becomes 1. And I was 1, and so on. And it goes on all the way up to 19, because we wrote 20 here. So it goes up to 1 less than that. And in the end, we print the value of k here. So essentially, this loop calculates this sum in the end. Okay. Any questions so far? Just write in the chat if there are any questions. Okay, good. Okay, so it's not always that you want to add just sequential numbers or use sequential numbers for this reason. So you might also have some kind of data. And one of the structures that you can use in Python to have any form of like numbers or variables is called a list. And I'm giving an example like conceptually here of a list. So I'm calling it my list. And the first number is 3.5, the second number is 2.1, and so on. So there are 7 numbers in this list, I think. And on this line, the top line here, I'm putting in the Python enumeration of lists. So I just told you in Python, you always start counting from 0. So the index of the first number is 0, the index of the second number is 2, and so on. So here, what I'm writing down here is I took the numbers that are in this list and I just wrote them in Python format. And you can see you've put these square brackets around the numbers and you separate them by a comma. So this is how you define a list in Python. So I just took these 7 numbers and put them in square brackets and separated by commas. And let's see if we can print this. And another thing, we had this type, print. So we can verify that this is actually a list. Type my list. And you can see, just as we did for the integers, Python will tell us what type it is, and this is indeed a list. Okay, so how do I access, for instance, I just want the first number in the list. So I call my list, and if I want to print the first number in my list, I can print, you use these, you use these square brackets, and you put the index of the number you're interested in here. So for instance, if I'm interested in the first, so I write 0 here, and if I'm interested in the third, so I put third in quotation marks, you put a 2. And if you have you want the last item, for instance, which has index 6, even though there are 7, you put 7 here. or sorry, 6. And we can see, indeed, we get the 3.5 as the first, and we get 2.5 as the third item, and the last item is minus 8.1. Okay, good. So now in this case, I knew that the last index was 6. So what do you do if you don't know the length of your list? So there's a function called len, which returns the length. So here we defined a list called sum numbers, and I just have I guess I have 6 numbers in sum numbers here, and here I print the list of the length of that list. So let's try and run that code, and it returns 6. Okay, so what is that useful for? One thing that you often want to do is, instead of going through all the numbers in a range, so for instance, range, you get like 0 to 20 or 0 to 19 here, you want to go through all the numbers in a particular list. So let's go down and look at an example of that. So here I write for I in range, and instead of defining a number here, I write the length of some numbers. And what I want to print is, I want to print every number in that list. So I write some numbers and the square brackets I. And it prints all the lists. So another way you could do this is you could just write in range 6 if you knew beforehand how long it was. But you could also use the length, because then you don't have to know this. So there's a question in the chat right now: are variables lists shared between the different coding fields? Yes. And I can demonstrate this just really easily. So up here, we define my list. So we could also print, so in this, let's do it in here. Print len my underscore list here. So basically, that's a really good question, actually. So basically, everything that we've defined in all our code fields, like for instance here, my var is John, we can actually access at a later point. So we could, for instance, print my var here. It should print John. Yeah, and that's what it does. Good question. Thank you. Where were we? Yeah. Okay, so here we printed every number in that list using this range and length. And there's another way, which is it's easier to write. It's a little higher abstraction level. So we have this list defined called sum numbers, 5, 10, blah, blah, blah. And we can actually say for n in this list, print n. And it would actually just go through each element in this list in the for loop. And because here we print every of that element, it will print that element. So there's another question. Yeah, let's do this and I can answer another question. So now we can see for n in some numbers, print n. So there's a question: what is the advantage of using print some numbers I instead of print my list? So these are just basic coding examples. So I wouldn't say there's anything better between using one and the other. So if you just want to print a list, I would definitely recommend that you use the print my list. So this is how I would do it normally, but this notation here, so that's just an example of how we can access it. For instance, we could also have used this to sum up over the numbers in some numbers for some mathematical operation. And we will actually do that later in this lecture during the example with the harmonic oscillator. Okay, I hope that answers the question somewhat. Okay, so one question. So this is the first debugging exercise. What happens if you ask for something that isn't there. So here I have, it's actually the same my list again. I just put it twice, just so you can see it in the same coding field. And as you remember, it has 7 elements, and you count from 0. So 0, 1, 2, 3, 4, 5, 6. And here I'm actually writing, give me the 7th element, which doesn't exist. So let's see what's happening. So now you can see you get a Python error, and you can see this particular one. So normally start by looking at the last line. So it says index error, and it says list index out of range. So the list index is what you have here, and out of range means that it's simply too large. Yeah, and you can actually see here above that, it will actually show an arrow that pointing to that particular line that was an error in. So I know if I had written this code for some reason for another project or whatever, that I had written something that didn't work, and it was in this line that that everything is wrong. So okay, let's go through this first, and I will answer a question about the ++ operator. Yeah. So now sometimes these error messages are quite cryptical, so you wouldn't necessarily know what that is. So what my recommendation is, copy and paste this into Google, and you literally just Google that. And also in Google Colab, there's also this this button here called Search Stack Overflow. We can try and press that, and then Stack Overflow is some kind of like internet forum where people can write questions, and so it takes me directly to a Stack Overflow page where somebody probably had a very similar error here. Okay, so there's a question: can I also use I++ like in Java? Yeah, so let me give you an example what you can do instead that is more Pythonic. Okay, so the question is, in C++ and Java and some other scripts, you can, instead of, let's say we have a value called k, and let's set it to 1. So in C++ or Java, you would, so if you want to add 1, sorry, my keyboard is fucked up, add 1 to k, you would use this notation, or you would sometimes use this notation, depending on. So the way I showed you in the beginning is called, you would do this, k equals k plus 1, which is sort of the standard Python way of doing it. Another way, which is slightly better, but I didn't tell you about, you can do like this, k plus equals 1. So both of these, let's call this c equals 1. And let's print k, and then let's print c. So we start with k, and we set k to k plus 1, and here we have c equals 1, and here we increment k by 1. And of course you can, let's do another number 3. So there's also minus equals 2, and multiply something by 3, and also division by 3 this way. So for instance, yeah, let's do the multiply by 3. So it should be pretty clear that if you take c equals 1 and you multiply it by 3, it comes out as 3. But yeah, to answer your question, Javago, you can't do this, as also somebody is writing in the chat right now. Okay, yeah. So I suggest you use either of these two that you feel comfortable with. So I'm using mostly this notation today. I know after the first 3 lectures, I think Guido, who is giving those lectures, he might use something like this notation. I'm actually not sure, but I can find out for the next lecture which notation he prefers. Okay. So let's go back to summation, because we're going to go to this coding example of the quantum harmonic oscillator in a moment. And then let's just see how we sum up over all the items in the list. So I'm just going to copy this here. I'm just going to copy this in here just so we can see it. Whoops, that was not where I wanted it. Sorry. Here. Okay, so we want to so we want to sum over all the items in the list from the 0th and until n, which let's say there are n, in this case 7. Maybe we can write 7 here. That would be more clear. So from 1, sorry, it should be, I bamboozled myself there. We would count from 0 to 6 if there are 7. So this is how we would do in Python. So we sum up everything, all our x's in this list, and we store that in this variable called y here. So my x's is, in this example, it's my list, the one we defined previously. And we can call, instead of y, we can call it a more Pythonic and more descriptive variable. So we called it mySum, and we let that start from 0. So there are 2 ways we can do it. We can just, for I in range 7, since we know that there are 7 elements here, we can, for instance, print my list, print the value of I, so the index, and we can also print the value of my list at that certain index here. Let me just add a space here. And finally, we can do mySum, and then we can set it to mySum plus the value of whatever is in my list at the ith index. So if we carry out this loop here, you can see only these 2 lines are indented. So the first iteration of this loop, of which there will be 7, the first one will it will take mySum and it will add the 0th element, and the next it will add 2.1, and then blah 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 and so on. And finally, after the sum is over, we remove the indentation because we want to print something that does not have to do with a for loop. We basically we print the result here. And apparently the result is 7.6 here. So this is basically how you carry out summation in Python in most ways. And we could also, if we didn't know that there were 7 elements in our list, we could have written len my underscore list here. And it will give you the exact same result, only more bug proof because you're not relying on your previous, like pre-existing knowledge that there are actually 7 things in this list. Okay, so this is basically some code that should get us all started with doing Python. So the next part of this lecture is going to be, if I can find it, it's going to be a coding example. And for this coding example, we will be coding how to do the quantum harmonic oscillator. So the quantum harmonic oscillator is basically an approximation for something like a diatomic molecule. So imagine if you have a diatomic molecule and you stretch it, the energy increases, or if you compress it, the energy also increases. And you can see on this graph here, there's this dissociation curve. It looks like, for example, you can call it a Morse potential or something. And you can see on the x-axis, we have the interatomic distance, so the distance between, for instance, the 2 nuclei in a diatomic molecule. And on the y-axis, we have the energy of that molecule. And as you can see, as you stretch it, it goes towards the energy goes towards the dissociation energy. And if you compress it again, there's the equilibrium distance down here. And then if you compress it again, the energy diverges towards infinity here. Now, so one of the approximations for this, which is probably most of you have seen that in physical chemistry or other courses. I know that you come from a lot of different places. So I'm just going to go through what that is. So the approximation is, essentially this is a kind of difficult potential to handle mathematically. So we can approximate this down here as a harmonic potential. So like an x, like parabolic curve, so like x squared curve here, which is much easier to handle numerically. And so if you do this and you solve the wave equation, the differential equations for this system, you'll find out that like through the wonders of quantum mechanics, that the vibrational energy levels are actually discretized. And one thing that you also find out is that the energy for each, so you can see like there's kind of energy levels here at higher and higher energies. And the energies of each states is given by this epsilon n, which is n plus 1/2. And this is in units of a bar omega. And one thing that we're going to assume in this lecture is that there are no degenerate states. So this is just to make everything easier here. Okay, so what we really want to calculate in the end is the heat capacity for this system. So I'm just going to go through all the equations that we'll be implementing to get to the heat capacity. Now, if you have a certain state, so we could call it the nth state. I'm just going to scroll up here. So the probability for observing the nth state at a given temperature tau in fundamental units is given by this exponential here. We call it sometimes the Boltzmann factor, which is minus the energy of that state divided by this tau. And then you divide by this normalization factor, which is called the partition function. And yeah, I'm writing the partition function here, or Zustandssumme in German. And it's basically a sum over all the Boltzmann factors for each state in your system. Just to make sure that this probability is normalized. Another thing we can find out is that the total internal energy, or what we call the internal energy. So that's the expectation value over all your energies. So basically for every state, we take the energy of that state and we multiply it by the probability of observing that state. Okay, so one of the first things we'll code is calculating how to calculate the internal energy. And as you can see, there's a summation here and a summation here. And that's exactly what we just implemented. So we will use the same techniques to implement those summations as we did here. So let's just go through all the theory part, and then we can get back to the coding. Okay, so another interesting property of this system is the heat capacity. So basically, how does the energy change as a function of the temperature? And it turns out you can write this as so this is called the second moment of the energy, and minus the internal energy squared divided by tau squared. And so I just wrote the internal energy up here, but here I'm just writing it again. So it's basically the sum over the energy multiplied by the probability, and here I'm just writing explicitly what the energy is, and still multiplied by the probability. And so this guy here is called the second moment of the energy. And it's calculated exactly the same way, except it's like the probability for observing the energy squared, essentially. So the only difference between these two is just this number is squared and this number is squared here. Okay, so let's get on with some coding examples. Okay, so the first coding example here, we have print the energy epsilon n for each state up to n equals 3. And I'm just giving the equation again here just for convenience. So this energy for a state of the harmonic oscillator is given by n plus 1/2. So basically, if we want to go up to n equals 3, so I'm writing it out very explicitly here. So Python always skips the last. So if we want to make sure that we get to the last, we have to at least loop over all n states up to 3 plus 1. And then for each of those states, we can make a variable called epsilon, and we can call that n plus 1/2. So just exactly what we write here. And then for each iteration in this loop, we just print that. And let's try and run that. I'm going to press play here. Okay, now you can see, so the 0th energy level, so the ground state level is 1/2, and then it increments by 1 every time, just as you would expect doing it to do from here. Okay, so now that we're able to calculate the epsilon, Yeah, also let me know if there's any questions to these exercises or the theory or something. Just write your questions in the chat. Okay, so example 2 here. So, whoops, there's an error in the headline here. So the next thing we want to calculate, what is the partition function z for tau equals 2.0? Okay, so if we recall the partition function, I gave it earlier, but here I'm just writing it again, just to clarify what it is. So it's these Boltzmann factors. So the exponential of the energy minus the energy divided by tau here. Okay, so there's one new thing in this equation, and which I haven't showed you. So if you want to use mathematical functions such as the exponential, those are not like built in Python directly, but they come from an external library. And usually we will be, at least for this course and most other places, I would say, people will get them from a library called NumPy. So the entire lecture on Wednesday, I believe, will be about NumPy actually and how to do math more advanced in Python. But for now, I'm just going to show you basically how to import stuff from NumPy. So the first line we write is import NumPy as NP. And what that does is it imports basically support for something that is in this library. And one function that it imports is called np.exp. And I just write here in like pseudocode that exp is the exponential function. So the way you call this is we imported NumPy as NP. So we write NP, and then we write dot. And from NumPy, we wanted to use the exponential function. And so here as an example, I just write the exponential of 0.0, which should be 1. And I'm also writing np.exp of 1.0, which should be the natural number e. So let's try and run this code and see if it works. And exactly that's what we get out of it. So NumPy has a lot of stuff in it. So we could also, for instance, print, for instance, cosine. It's called np.cos of, I don't know, 23.8. I don't know what that is, but that's definitely a number that we can print. Yeah, later we will look into on Wednesday, we'll look into the documentation more clearly and see how we get mathematical functions. And we can also use it for matrix algebra and vectors and linear algebra and stuff. But for now, this is enough. So let's just delete this here. So now that we've done this in a coding field, NumPy is actually imported for every single field in our entire Jupyter notebook. Okay, so now that we have access to this exponential function, so let's calculate this zeta or z, the partition function, just like we calculated before, everything before. So now you see that this goes up to infinite, and this is an exponential function. So it means this minus this gets higher. Yeah, the contribution from each element in the sum will get smaller and smaller. So instead of infinite, we can just write a really large number. And I think in this example, I write 10,000, but we can just say 1,000, and it shouldn't really matter. So we're going to do the same thing as we did before. Yeah, and I'm also defining the temperature tau here. So let's just do exactly as we did in the example up here where we did summation. So let's do that again. So we basically set the starting value. Let me do like, yeah, now everything is in the screen. So we set the starting value of z to 0.0, and then we loop over every state here in our function. And then for every loop, we add this amount to the partition function. So you can see I'm writing np.exponential, and then I write in the parentheses. So you can actually see where the brackets open and close for this function, which makes it more convenient to do. Here I write minus, and then I have n plus 1/2, just like I have here, and then I divide that by tau. And I do that for every state, so I'm doing that 1,000 times. or 1001 actually, because I have one extra here. And then finally, we print the petition function here. So let's see what happens. And as you can see, it does 10, or it does 1,000 loops in like virtually no time. And you can even set this to, let's do 10,000 as it was initially. Yeah, and we should get virtually the same number. It's actually the same number to the decimal, because the last iterations, basically this amounts to 0. Okay, so now that we actually did this, we have the petition function for this specific temperature. Okay, good. So let's go on with the next example. So the question here is then, with all that in mind, what is the internal energy U for tau equals 2? So if we remember, the internal energy was the expectation value of the energy for each state. So I'm getting a question if I can briefly talk about numerical accuracy. I will take that question in a bit. Just give me 1 second. Oh, okay. So the question I'm getting is, what is the difference between like the extra loops here? That's actually a good question. So I showed you. So let's do a numerical test. So let's do just something ridiculous. 10. No, let's stay with 10,000. So we actually have an exercise on this tomorrow, but let's see what the difference is between the different the different n that we sum up to here. So basically, we know that every loop iteration, we add this amount to the petition function. So basically, we could keep track of what that amounts to. Print here. So if we print n, and if we print this contribution, let's do that for every iteration. We should actually be able to see. So like to the computer, yeah, now we're printing 10,000, so that's a bit much. But now we can scroll through all the iterations here, and we can see that I'm almost running out of space here. Yeah, here we go. Okay, so it only prints the last 5,000, which is fair. So let's try and do that again with 1,000 here. So you can see for the last 1,000s, this amount actually amounts to something like, that looks like to the computer like 10 to the minus 200th. So very, very small number. And let's see when it actually becomes insignificant. Here, if we can scroll up a bit again. So actually the internal accuracy of the computer is like 10 to the minus 14th to 10 to the minus 16th. And we can see actually already after 60 iterations, we get below that. Or maybe 70 something iterations, we get way below that. So actually we just need to go up to 100. Let's do this. So we can go up to 100. So we can, let's save this. So 100 gave us, and then we can write 1,000 here. And then we can write 10,000. So just to see if there's any difference here. So this is for 1,000. And let's do 10,000. Just you can see the trend. Here's, let's run for 10,000. And those numbers are exactly the same here. Yeah. So tomorrow we'll have an exercise on how to actually find out when to stop for loops and when the numbers are or sufficiently low for breaking these for loops. Okay, I'm just going to set this back down to 1000. Okay, so now we have done that. So let's go to the next example. So the question here is, what is the internal energy U for tau equals 2.0? And so the internal energy U was this expectation value, and it's the sum over every state, the energy and the probability of observing that state. And just also recall that the probability of that observing that state was the Boltzmann factor divided by the partition function. Okay, so we already calculated the partition function z here. So this is already stored in the memory of our computer. Okay, so we can basically just use that every time here. So now to carry out this summation here, so every loop we have to calculate this epsilon, and we have to calculate this probability here. So let's start U. We start at a value of 0, and then we loop over all the states that we want to sum up to, and we just, as we just looked at in this here, n states equals 1000 is fine. That's way beyond the accuracy that we can get with the computer. So we calculate again here, the epsilon for the nth state is n plus 0.5. And then this means that the probability of the nth state is then, so the exponential of minus epsilon divided by tau, and then again divided by z. And then, so those are those two numbers. And we have to add those to U. So we can say U equals U plus epsilon times probability here. Yeah. So essentially, yeah, let me put this on here. So we actually print every, just a second. Yeah, so we print every iteration. Okay, so let's see if we can make any physical sense of this. So the zero, for the 0th state, the energy is 0.5, and this is the probability of observing that state. So this is about 39%, and the next state is 1 and 1.5 and blah, 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 and 23% and so on. And as you can see, the probability for observing a state actually, as we go higher and higher in the states, it becomes clearly insignificant at, yeah, very fast. Let's remove this, and let's print the energy. So the total internal energy for our harmonic oscillator at a temperature of tau equals 2, it seems to be 2.0. Okay, so in the last example here, before we calculate the heat capacity, yeah, so if you remember the heat capacity, I'm just going to scroll up a little bit more. The heat capacity is the second moment of the energy minus the expectation value of the energy squared divided by tau squared. So if we want to calculate the heat capacity, we also have to calculate the second moment of energy. And just for lack of imagination, I call this U2 because this is the second moment of the energy, U. And I do that the exact same way as before. So I started with 0, and I make the sum over all my states, calculate the energy, and then I calculate the probability. And here to U2, I add the energy squared multiplied by the probability. So instead of just the energy like we did for the expectation value of the energy, I add the energy squared here. Okay. Yeah, and I don't think we have to print. I guess we can do it just for, so we can print every iteration here. And let's just see some of the first. And you can see they have the exact same probabilities because it's the same system. And we just went through those. So let's comment this out. And so if we do this, yeah, it turns out the second moment of the energy is about 8.08 something here. Okay, so now the final heat capacity, we basically calculated U up here, and we have U2, and we also have tau stored somewhere, which is 2.0. Then we can calculate the heat capacity here. And the heat capacity for in these units is about 0.79 or sorry 979 something. Okay, so this was kind of a demonstration of like all the things that we have gone through today. So if you're really interested, there's an extra code snippet here where you can actually calculate CV as a function of tau. So this is something I would encourage you to go through alone after the lecture, see if you can understand this code and see if you could like try and run it and change the temperature and see if you can like tinker with it and see what happens. So this code is kind of ugly in the way it works. And tomorrow we're going to look at something called functions and how to define functions for this. But for today, basically this is about the end of the lecture. So hopefully you've seen how to do summations now and how to see or how to do basic things. And this is exactly, you'll be going through these techniques of summation and stuff in the exercises. So maybe I should give a short introduction to the exercises also before we stop for today. So let's go to, let's open the exercises here. So I go to, they were stored in the same place as the lecture. So let's go to GitHub here. So we can write andersx Python. Oh, they're already there, intro here. And they're already there. So now to get to the exercises, instead of pressing the lectures, we just press the exercises and it should, we can actually, let me just save this, save a copy and drive. So so let me give an introduction to the exercise here. So the way they work is you go to GitHub and Python intro here, press enter and it should come up here. So the exercise is also an IPython or Jupyter notebook here. So let's open the exercises here. So the exercise is in the form of a worksheet. So for example, the first exercise is extremely simple. I think every one of you should be able to do that yourself. So for instance, so every exercise has an example and then basically do the same thing yourself. So here, you just have to change this line to write a code, to write the code for setting x equals to 3.5 to the power of 6. I think most of you should be able to do that. And then there's an example of summation. And then here, question 1.2 and 1 is doing your own summation. And then there's a debugging exercise where you have to fix some errors in this. And so on. And so to do the exercises, you open this worksheet from GitHub and then remember to save it in your Google Drive or save it or download it or something. So you have it for posterity. So there's another question. Could it be that in the last exercise there's a mistake with the sum because 0.0 or 0 to the power of 0 is undefined? I'm not sure. So this is from Oliver K. I'm not sure what you mean. Let's go back to that. So which exercise do you mean, Oliver? So let me just look at the last exercise here. So someone is raising their hand. Hello? I unmute you. Hello? Okay. Okay, so the next question is, how can we hand in the exercise? Okay, that's also a good question. So these exercises, you don't have to hand them in. So there are 3 lectures. So every lecture of mine, so I have the first 3 lectures, so Monday, Tuesday, and Wednesday. and after each lecture, there's exercises, and you don't have to hand these exercises in. So in addition to the third exercises, there's a small set of exercises which you have to hand in. Maybe I can put that up here. So here, if you can see, so there are three, so there's this final graded problem set. And the way that will be handed in is there will be a multiple choice test online where you can enter the results from each question. So we're still setting that up with the IT department. So unfortunately, I can't give you a link or like say anything exactly on how that is going to work. But I will give that information to you as soon as I have that. Okay, so he means question 151. So it's very likely that yeah, so let's try to run that. So 0 to the 0th is undefined. Yeah, I guess that's, so I guess a convention in Python is just, I actually don't know what happens here. So 0 to the power of 0. So apparently, according to Python, this is 1 here. So this is just the mathematical definition, or not the mathematical, it's just the implementation. It's not the mathematical definition. This is how it's implemented in Python. So that's just how that works. Yeah. All right. Yeah. So are there any further questions? So there's another, oh yeah, there's actually one more thing. So there's a question, what about the additional exercises for the practical course? So the practical courses, you should receive an email at some point about those because I'm not in charge of those. But that's definitely, I can ask for tomorrow about more information about the practical courses, but since I'm not involved with those, I actually don't know. And so maybe there's one extra thing I want to talk about. So you should all have received an email about this link for, let me just move my windows around here. So we set up this, it's called Slack, and it's basically, it's like a forum or message board where you can talk about, it's mostly directed to people who talk about code. And this is basically something we set up and invited you to. So you should have gotten an email last night with instructions on how to, there's an invitation link that you can click on, and I see, let's see, yeah, people, at least 23 people have signed up for this. And so this is basically an extra service that we provide. So for instance, if you have questions about the Python intro course given by me, maybe I can zoom in a little bit. You can go to, there's a channel for that, and you can ask questions, or you can ask questions directly to me or to the other students, and you can discuss with each other. So this is just something I would recommend that you all use, so you can like collaborate on making this course as efficient as possible. So could you send the code again? Or which code do you mean, Nadia? And also, are the lectures on Tuesday recorded for those of AC4 that have other seminars? Yes, I will upload them, all my lectures at least, and I will send that link out. Yes. Let me find the link to the form. Copy. So it should be in the chat now. There should be a link that you can all use to sign up for this Slack forum. Yeah. Yeah, someone just signed up because there were 23 members a while ago. And 2 more. Okay, so yeah, so for tomorrow, I suggest that you go through these exercises. Feel free to collaborate or talk to other students about it, and use the Slack forum and everything. And yeah, so basically see if you can do as many as these exercises as possible for tomorrow. Yeah. So there's one more question. I'm very unfamiliar with Google Drive. I don't quite know. Can I save? So if you don't want to use Google Drive, you can just download the IPython notebook directly and save it on your computer. And when you say open, you can just you can upload it from your computer here. So there's another question. Do you know how to switch between different Slack workspaces? As we already have a Slack workspace for the research group. I actually don't think you can be logged into two workspaces at the same time. I think you have to log out from one and then log into the other. I think that's usually how it works. Okay, so I will check the Slack workspace periodically. So if you have any questions, yeah, I would suggest that you go to this Python intro channel and you can write all your questions there, and then I can answer the questions there, and then hopefully it will also benefit other students if they see those questions. So yeah, I think that's all for the lecture today. Okay, so I will stop my screen share from here. And yeah, thank you for today, and I'm looking forward to seeing you all again tomorrow. Bye.